this final part. Perfect. Before I dive into this final part, is it okay to have a show of hands on the chat for whoever attended either part 1 or part 2? And to raise your hand, you just go on Zoom, the 3 dots on more, and raise hands, just to get a sense of, you know, there's a very short recap, but just to get a sense of how much of a recap we might need to do, and if I need to direct you to other resources. Okay, I see a few hands up. Oh, it's coming. Okay, great. So a few hands up, but not as many. Okay, so then Romy, are you able to drop in the chat for everybody the link to the recording?
I'm sorry, I lost you there for a second. What was that?
Would you be able to place in the chat the link to the recordings for session 1 and 2?
Yes,
so
I will do that right away.
Have the link. Yeah, okay, so that attendees have the links, just the as we're building up, you know, for the different sessions. If you've missed part of it, you know, you get to look back at it and hopefully make a little bit more sense of it. So, okay, great. So today is part 3, and we're going to focus on the building enclosure. As a quick reminder, we had part 1, which was an overall introduction of Passive House, and part 2, which was focusing on the changes in design and construction processes. So more of the soft skills and how to guide the teams to deliver high performance buildings. Okay, so let's get going. I'm Marine. I'm the Passive House Service Lead at RDH Building Science. We are, I'm based in Toronto, but I do practice and lead projects for North America. And as you can see on the screen, so we have offices throughout North America on the East Coast and West Coast. And we offer several services. We started from a building enclosure background, but added a strong energy and sustainability group. But we also do research. We have a good lab in Waterloo, and so we keep learning between enclosure work, new and retrofit, energy work, and research and development to kind of, you know, sorry, I'm searching for my words, kind of a continuous improvement loop. So that makes it quite interesting. Right, here we go. And just in terms of Passive House, because we're talking about Passive House today, so we've gone through a fair share of projects at this time. We've got experience with, you know, I would say almost every single typology, so we can do any high performance buildings. But what is again really nice in the delivering these high performance buildings is that we can add both our enclosure and our facade work with it to enhance the whole deal and make communication a little bit more efficient. And as a side note, we went through the certification process in part 2, and you know that Passive House is one of these green building certifications that does ask for a third party, an independent third party verification, and we are accredited to do that for Passive House. So when we're not designing, we can get the role of certifiers, which is your third party verification. Okay, so the plan for today, this one is a bit more geeky and focused on the enclosure, so I think this I'm excited about this content. We'll start with looking at opaque assemblies. We'll then keep going with thermal bridging, which is a new, kind of a new flavor added to the calculations that the industry has been used to doing. And then we'll finish with, a closer look on the windows before moving to the Q&A. And in terms of Q&A, so I'm just seeing the chat as well, feel free to put your questions in the Q&A icon, and then we'll review all of them at the end of the session. So don't wait, you can just dump them there, and then we'll review them together. Learning objectives, again, you have seen that on the on the email and the registration, but again, we're going to focus on understanding the definition of the clear wall R values. We're going to zoom in into thermal bridging to understand, what are the key typical thermal bridges to consider and how you judge their impact. And finally, looking again a little bit more closely at window performance, window U value, window R value, and how we define that performance. Okay, so just before we dive into the opaque enclosure, I just wanted a very quick refresher, especially as a few people haven't attended the previous sessions. So as a reminder, we saw that in part one, the Passive House key principles are around the 6 key bullet points: compact massing, a lot of insulation, but a thermal bridge free design, so no gaps into your insulation layer, and airtight building, high performance windows, as well as ventilation, mechanical ventilation with heat recovery. And what we're focusing on today is the enclosure, which is highlighted in blue: thermal insulation, a thermal bridge free design, as well as high performance windows. And so just before we dive into, again, the enclosure, the second part of the refresher regarding Passive House are the key metrics, just so that we are all speaking the same language when I talk about energy budgets. What you're going to see from the bottom to the top are the key criteria to meet to reach Passive House certification. And again, you can dive into part one. We went through all of these criteria at a much slower pace. But as a refresher, we still have that TEDI, the thermal heating demand, which we call space heating demand, and space cooling demand, so no more than 15 kilowatt hour per square meter per year. So this, if you see my mouse, the bottom one, the heating and cooling demand, this is where we're making the most significant reduction in typical compared to typical buildings in heating and cooling demand. We do have a whole building tightness target, which is a pass-fail criteria. If we were not to have cooling, which is not really often in new buildings, the more we with climate change and changing weather, I think most buildings are now designed with that, so that criteria does not apply when you have cooling. You go back to the cooling demand. And finally, the primary energy renewable, which is a very Passive-centric metric, but even if it looks a bit weird, it's simply a combination of your EUI, your total EUI, your energy use intensity, which is the total energy consumption of your building, with the GHGI, which is your greenhouse gas intensity. So it's really looking at your EUI, how much is your building using in total in terms of energy, and then adding adding a carbon factor to penalize any fossil fuel source of energy that you're using, or help you with any cleaner energy sources, right? And so with these criteria that we have to meet for certification, and these gets calculated through the model, these are what I call our energy and or air leakage budgets, right? The air tightness is your air leakage budget, and both the space heating / space cooling, as well as the PER targets, are your energy budgets that we're trying to manage. And so these, when we're trying to manage these budgets within the allowance that we got given, this is why we need a good enclosure to get us there, hence the focus of today. So diving into opaque assembly performance. Okay, so there's that question of, are we speaking the same language? And with high performance buildings, we need so much attention to detail that even if at a high level we think that we're speaking the same language, more and more, even with great design teams, you start seeing certain subtleties that might be, lost in translation or lost into the details or lost into the drawings. And so with these small gaps, they can add up to quite a lot and have an impact on the performance of your building. And when you're designing all the way to Facades performance levels, the targets that you have are quite stringent, which means that you don't have a lot of buffer to, to allow for these small misunderstandings to catch them after the facts if it's not what you had planned. So that slide, always looks a bit funny, and people are like, really, Maureen, does that really happen? But it does. So quick example to start with, which really matters with the vocabulary that we're using around opaque enclosure performance. When we talk about R values, right? Everybody lists everywhere in their drawings, in their specification, the R value. But which one are we talking about? Because they are a lot of different, R value definitions. What we used to work with before was what we called the nominal R value. And it's the R value, so, the R value, the thermal resistance, the performance. And so when the performance of the insulation. And so when we talk about nominal R values, we're focusing on the insulation layer only. So we're almost we are disregarding the rest of the layers in your assembly. So not quite characteristics of exactly how your wall is performing. What the industry is, used to doing, and used to, the term that is being used is the assembly amount. So you're looking not only at the nominal, but you're adding all the thermal resistance of all the other layers. So you're still looking at you're now looking at all the layers. That's much better. However, the cut through which you're looking at the cut that you're doing where you're looking at all your layers, the cut is then in the best scenario you can think of. So that assembly R value might look pretty good, but your wall performance is not just through the best cut. For example, if you look on this, if you look at, we have a few people in the office today. So if you look at that example, you're going to see that we have cladding attachments that are going through the insulation to support the cladding back to the base structure. And so the effective R value that we're looking at, which is the clear wall R value, we're now going to consider the impact of absolutely everything. We're not only going to look at every single assembly layers, but we are also going to include the derating impact of any repeating thermal bridging. These could be cladding attachments, as you're seeing on the screen, but it can also be, steel stud in an insulated steel stud backup walls. So it could be insulation fasteners. So anything that keeps happening into your wall, we're going to have to include it to describe accurately what is the actual performance of your wall. So the question is going to be, well, Maureen, do you think that really makes a difference? What is the type of difference, what is the amount of difference that we're seeing between assembly R values, so not derated, with repeating thermal bridging, and clear wall R values? And this can be quite a lot. What you're seeing on the screen is a table, and as on the y-axis, all the lists are different types of cladding attachments. You're starting at the top from the worst performing ones, all the way to the bottom with the best performing ones. And the x-axis, the percentage listed at the bottom, it is showing you that if the wall without these cladding attachments would be 100% efficient, whatever the U value or the R value that you're aiming at is, what would be the derating in that R value once you include the impact of the clips? And what you can see is that, yes, in the orange band, we have a few options that are very performing. The derating is between, no more than 5 to 10% derating. But as soon as you get into, larger clips, stainless steel clips, sometimes fiberglass clips, so non-conductive clips, but still with conductive screws, right? Be it either galvanized or stainless steel screws. The impact can range anywhere between, 65 to 95% performance. So, we're in the 10 to 30% derating. And you can see that if we go back to, continuous conductive Z-girts, then you're really you're not seeing much much value for the money you put into that insulation layer, right? So this is the theory behind it. I thought I would enhance today's presentation with a few examples that we've got in the office. So the first one is the University of Toronto Scarborough Passive House student residence. This one is currently under construction. It's going to be completed at some point in 2023. I've highlighted roughly the program. So we're talking almost 800 student beds with a commercial level 1, including a large commercial kitchen, as well as other type of amenities and teaching spaces. You have the performance on the right, and you can see the floor plate at level 2 and above, where you see a lot of student residents, and the level 1, including the terrace where you're seeing in green. So what is the wall performance and what is the wall assembly that we're working with? As you can see on the screen, right is inside, left on the detail, left is outside. And so the insulation layers, the layers that are bringing, the thermal performance to your assembly, are highlighted in blue. And you can see you have a 6 inches, that's a bit more, 6 inches insulated steel stud backup wall as your backup structural layer. And you have a 6-inch mineral wool insulation externally with non-conductive fiberglass clips to support your cladding attachment, right? And so this provides you with a total clear wall R value of R33. So that's the effective, right? So that includes the derating impact of all the clips I'm putting through my insulation layer, as well as the steel studs. And so just to highlight why it's important to capture them and why it's important to think about them really early. In the design, I'm just showing you the design progress through that project. In the design, we got told from the architectural team, let's use a 24 by 32 spacing that is equivalent to 2.8 clips per square meter. That's just the way our energy models work. Just to be a bit conservative, knowing we're going to have corners, we're going to have a few things that don't align with the exact, spacing. I said, okay, I'm going to take that down to 24 by 24 just to be conservative. That's a 2.1 clips per square meter. Then we received the submittals, and the submittals were way higher because of all the additional support that we needed around the windows. 3.3 clips per square meter. So that was starting to have much more of an impact to our effective R value. And then on site, because Passive House, you will have seen through part 2 of this series, Passive House is not based on the design intent that we have. Passive House is one of these few certifications that is based on what we deliver, product that we deliver. So we have to back up every single model assumptions with the site evidence, collected during the construction phase. And you can see that the installation is currently ongoing. So you can see some of these rows are already done, but they haven't finished everything around the windows. So we're still awaiting patiently to know exactly what will be the final number of clips to capture that into the correct clear wall, effective R value. And so through the submittals, we started at 3.3, we were able to fine tune it a little bit better. And where we landed is that the difference that you would have with the clips and without the clips reduces your R value from R35 to R33 because of these non-conductive clips at a fairly large, it's not the largest, we can do better depending on, the loads that your cladding is facing, but it's not the tightest spacing that we've seen. So just to give you an impact of these highly performing clips still making a difference to your overall R value. Again, just another quick example, this time on the West Coast. This is the University of Victoria student housing and dining, so very similar archetype, but climate zone 4. And you can see that because of the change in climate zone, it's a lot, a bit warmer over there. Winter is not as demanding, and you're seeing a slightly different. Sorry, I lost my mouse. Here we go. A slightly different wall assembly where this time our backup wall is uninsulated. Why? Because the steel studs, when you place insulation in your backup wall, the steel studs create a very large thermal bridging. So you will never get a lot of, again, value for money with doing an insulated steel stud backup wall. So this time, to save money on, material, but primarily installation, they decided to keep the cavity, the steel stud backup wall uninsulated, and simply increase the external wall insulation from 6 inches to 8 inches with, again, a firmly broken clip, right? And so that gives you, again, an effective, a clear wall R value of 134. Again, showing you what that means when you look at it on site. It's a lot of, attention at, vetting the clips that we're using, double checking the spacing, from up close with tape, with a tape measure, but also from far away to make sure that we are seeing exactly the spacing that we're after. What you're going to notice in the middle and right picture is that not only we have the larger, rectangles, which is like the face of the firmly broken cladding attachment clip, but you're also seeing little dots of shiny metal, which are the stick pins used to hold the insulation, so insulation fasteners. And what you're seeing on that project is, again, taking into account a fairly good spacing of both the cladding attachment clips and the insulation fasteners. The clear field, the clear wall R value over walls is reduced from R36 to R34 with these high performing products. So clearly the more not we lower, but the worse the performance is going with these cladding attachments and insulation fasteners, the more of an impact it's going to get onto your clear wall R value. Okay, so I started looking at the, at the larger surfaces, mainly the walls, but you can see that the same approach is going to be used for, your floor, for your roof, for your soffits, if you have any, for your parking ceiling, if that represents the thermal floor, the thermal delimitation between inside and outside your building. So we're looking at all these big surface areas of opaque enclosures in a similar way. But there is more than just these larger areas of enclosure, right? And this is what we call thermal bridging, which mainly thermal bridging will happen around interfaces, as we'll see in a second. So just before I go through that slide, I want to confirm, I want to reiterate the definition of a thermal bridge. Again, we saw it a little bit more in part 1, so you can always go back to that session. But A thermal bridge is simply a discontinuity in your insulation layer. So it's a gap. If you were to, trace your entire insulation layer like we've done on the screen, the different colors are just for different assemblies, you should be able to, even with the details, to never lift your pencil up. And the truth is, the way we built it will happen a few times, and this is where you're capturing the thermal bridging. So what are the key thermal bridges that we want to pay attention to? It's mainly at interfaces between different elements. So we're going to see, parapets, we're going to see intermediate floors, we're going to see, windows and doors, balconies, at grade perimeter, and the slab perimeter, right? Again, the perimeter of your elevator pit as well. So they are quite a few in there. And then if you see just that quick section of one of the buildings we're working on, you also see that, between the external wall to the parking soffit, and then around the ramp, because the ramp is excluded from the thermal area. This slightly deeper is going to be the elevator pit. So you really have to think, and same thing at on the top level, going around the mechanical enclosure, if the mechanical enclosure is part of your thermal enclosure, right? If it's considered inside. And what you'll see as well in that list is that some of them are more point thermal bridges. So for example, roof anchors or HVAC equipment, the way we support all the roof mounted HVAC equipment through platforms. Every time this might go through your roof insulation, this is more of a point, it's one location where the thermal bridge happens. The same with, plumbing stacks and some of that. So having said that, I'm sure that most of you already have a pretty good idea of, where thermal bridging might happen. What I wanted to do today is making sure we go a bit deeper in the understanding of how do we capture them in an energy model? How do we understand their impact? So, diving in. What we're used to, do you know when we call doing high-level heat loss calculations or U times A calculations, this is what we're talking about, right? The overall heat loss is most of the time simplified to the heat loss per unit area times the area, right? So you remember the large surface areas where we're talking about walls, roof, floors. This is typically the simplified approach. But now that our energy and carbon targets are getting a lot more stringent, we have to pay closer attention to the enclosure, and we cannot forget the impact of thermal bridging, which happens in real life, independently to if it's captured or not in your energy model. And so the truth is now the overall heat losses has to be the addition of these three elements, not only the large surfaces, but also all your linear thermal bridging, as well as all your point location thermal bridges. So just to give you a quick example, the top one is looking at areas, walls, floors, roof. The second one is going to look at length. So this is the length of your interfaces, for example, your parapet, your intermediate floor. And then the heat loss per unit is going to look at, point thermal bridging, which happens in one location, such as, roof anchors. So what are you seeing through that calculation? The column on the left represents the performance, while the column on the right represents the quantity. And hopefully you're all gonna, recognize what is that heat loss per unit area for the first one. What is the one that we're used to? This is your, U value. We're talking about U value right now because you have to combine U with A for unit purposes, but you know that it's the inverse of the R value. So when we talk about U times A calculations, if you've ever heard that, it really means that U value time, which is your heat loss per area times your area to get back to your heat loss. So this one, you'll likely be very familiar with. But when you move to the next portion, we're now looking at psi values, right? And this is what is descriptive to the performance of these linear interfaces, right? Linear transmittance captured through a psi value. The psi value gets multiplied by the length, and again, we fall back on our feet with being able to add them apples to apples. And the third one, I'm sure you've guessed where we're going with that one. We're talking about chi value point transmittance, which we then add up with the number of points, the quantity that we're using. So I'm going to pause here for just a second so that everybody can, review that slide and digest it. But when we look at the overall heat loss throughout our entire enclosure, it is the sum of the larger surface areas plus the linear and the point thermal bridging. And the way we win at this, because you understand that even if all these additions of linear and point thermal bridges might be very small, you might end up going through, death by 1,000 cuts, right? A little and a little and a little starts adding up to a lot, especially when your energy and carbon budgets become really stringent. So the way we win at this is making the area on the left, which is related to the performance, we make this better. So a better enclosure performance, or a smaller thermal bridge. And then we make the quantity through areas, lengths, and point connections as smaller, as few as we can. So when we're attacking that enclosure overall performance, you really have to look at both aspects of how far can I push the performance, but also how can I consolidate my design so that I am penalized through these derating, right, through these additional thermal bridges as little as possible, because it all adds up to your energy budget. And if you decide to spend more of your energy budget on thermal bridging, this might be that you can spend less on your window to wall ratio or on other things that most design teams will consider more important. The final thing I'm going to say on thermal bridging before moving into sharing a few case studies is the accounting of thermal bridging is into energy models and into energy performance results. This is something that will become the norm. So for example, for anybody practicing in Toronto or in BC, for example, the Toronto Green Standard and the BC Energy Step Code are clearly stating that for energy modeling purposes, thermal bridging should be accounted into the energy models. So this becomes the new approach, the new basis of design. And by the way, the national codes are going to move that way as well. Similar things with some of the municipalities and regulations in the US. This equation on the screen and this approach is what actually happens in practice. So this is helping us have a more accurate prediction of how the building will perform. So even if you might not have to do it today, know that this is where we're going. There's no question there. Okay, so giving you just a few case studies before we finish on the window section. This is a slightly smaller multi-unit residential building, 9 stories, 64 units, so fairly straightforward. You can see the performance. And what I wanted to highlight on this one is, first of all, just to highlight that we can do passive house with almost any type of assembly, right? Passive house is not prescriptive to a certain wall assembly. So you're going to see that that project is using precast sandwich panels, 4 inches of phenolic insulation in the middle with non-conductive ties tying the external leaf to the internal, in this case, structural concrete leaf. That gives me an R31. But, you know, so just a small flavor and a slight difference from the other case studies that you've seen. But what is more important for today is the thermal bridging. So you can see a parapet on the screen. So you see the architectural detail on the left, the thermal bridging model, you know, the visualization in the middle, and the results on the right. And so just to help as to how to read some of these thermal bridging results, when you're looking at, you know, the rainbow colors with all these lines, every line is called an isotherm, which is a line of similar temperature. So the purple one is going to be the one completely outside, and the red one will be the one completely inside, so warm and cold. And so as you can see, the isotherms are not moving really nicely together. They're kind of getting stretched everywhere, which means we're having quite a lot of heat losses. But it's much better than if we didn't have that additional insulation. So I don't know if you looked at the detail a bit more closely, but you can see that the external wall insulation, which is my, you know, sandwiched insulation in my sandwiched concrete panels, has somehow to connect with my roof insulation. And this is done with the addition of both, you know, return parapet insulation plus some insulation at the cap. So of course we have a bit of, you know, timber and other support, but mainly we are tying the wall insulation to the roof insulation with a small, you know, detour, which gives us a, you know, non-negligible but still small psi value for the parapet, which is great because for that particular building, the massing wasn't really compact, and we were adding quite a lot of length onto that length of that parapet from the bridge. The other example, which is you know, pretty interesting when I put this presentation together, this is another multi-residential building. We're looking at a bit upwards of 150 units, 2 buildings tied back together. Again, just before I go into thermal bridging, a different wall assembly again. We are working with an insulated, 6 inches insulated steel stud backup wall, but externally we now have graphite EPS adhered. So we're working with an EPS system. So no cladding attachments because of no cladding, which means no derating, which is great. And that can be seen through the R38 clear field, you know, clear wall R value, which is a bit higher than the other ones we're looking at. But what I wanted to show was the panel joint thermal bridge. So why am I talking about panel joints? I'm going to skip to the next slide and come back, but this is the zoom, the snapshot on one of the facades, and every single blue line is the outline of panels because we will work with a panelized enclosure on that particular project. Even if it's a little bit new, the industry is pushing towards, you know, panelized assemblies, and we can do passive house as well. But with that in mind, this is the detail of our panel joints where you see the 2 backup walls tied together with a small pin, and then the external wall insulation kind of connecting with each other with a bit of spray foam in between. So all in all, a very good detail, which you get to confirm through the psi value. 0.01 is a lot smaller, you know, 0.01 watt per meter per Kelvin is a lot smaller than the parapet thermal bridge that we just looked at. So great, thumbs up, we have a really good detail. It's a really low psi value. We're really happy about that. But when you look at the facade and you start adding, you know, it's 2 of these buildings, so, you know, 4 facades like this that you're looking at, plus the thin ones on the side, it adds up to 3.8 kilometers of panel joints on that job, which adds up almost 2 kilowatt hour per square meter per year of heat losses. So I don't know if you remember, but the target that we have for space heating demand is 15 kilowatt hour per square meter per year. And that's the heating demand. And when you look at the total of your losses, it might be anywhere between 30 to 40, 45. So 2 kilowatt hour per square meter per year is not negligible. It makes a difference. So you can see that's an example of a really good thermal bridge. So meaning it's minimized, but because the length is so important, it adds up to a very impactful amount. And finally, we're going to dive in with, we're going to look at windows a little bit more closely, because everything we've talked up to now also does apply to windows. We've seen this during part one with the window R value, right? So window performance is described through your window R value or U value, depending on if you work with SI or Imperial. And what the industry mostly captures into that window performance is the impact of three different elements. The impact of your glazing, which is done through your center of glass U value. The impact of your frame, which is done through your frame U value, so UG or U center of glass and UF respectively. And then as we're moving much more to double glazing, even triple glazing for meeting the most stringent targets we have at the moment, and passive house targets, we are working with double or triple glazings, which means you need that spacer to separate the panes of glass. And therefore, you do have a little bit of additional heat losses happening through that space apart, right? And this is what the industry considers your window performance, but that is not all. That is missing one key element, and it is the installation part. So same thing as with thermal bridging, linear and point thermal bridging to be added to your, larger wall surface areas. Window installation also has to be added to, let's be honest, either the window performance or the wall performance, but it should be accounted somewhere into your energy model, because additional heat losses will happen at that interface. And you know better than anybody, I'm guessing most of you are architects on the call today. That is a tricky interface to detail, and it's never going to be done 100% perfectly. So you will have these additional heat losses that you should capture, because that is what code and model requirements are asking you to do. Again,
Hello, Maureen. I'm sorry to interrupt you, but we've lost your sound considerably.
Oh, that's very interesting. Okay. Is that any better?
Do one more test for me?
Yeah, 1, 2, 1, 2.
Yes, that's much better.
Okay, don't hesitate to keep interrupting me. I have the other headphones, so we can change anytime.
Okay, thank you.
Okay, I'll keep being loud. So just finishing with that case study. So you remember the University of Toronto passive house residence? Well, we have 800 beds, and you can see one of the typical elevations of that U-shaped building. So one of the external elevations. You can see a lot of windows, so you know where I'm coming with this. On that particular project, we are looking at a total of 5.3 kilometers of window installation, more than 1,000 windows. And that adds up, again, back to our metric and energy budget management, plus 1.2 kilowatt hour per square meter per year for the windows only. And so is that a lot. Well, that's a non-significant, you know, sorry, that is a significant impact. Was it because of the performance as well as the sheer quantity of windows, like total length that we had? And the truth is the performance was already pretty good. I'll push you back to session 1 again, if you want to hear a little bit more on that detail. I did present it there, but the window installation, as you're seeing on the screen, you can see, so the results with the isotherms on the right, the sketch, the detail on the left. You can see the backup wall at the top. So the top is inside, the bottom is outside. So backup wall. And what we're doing is that we are strapping the window for a strapping core, spray foaming the gap that is left after the backer rod. And then once we've done that, which is already quite good, we are actually installing external wall insulation for 6 inches that we have on that project, with additional insulation highlighted in that light blue rectangle. We are putting insulation in front of the frame to protect it further. And then we are tying our window reveal back to the clips, which is that dotted line. So we have a really strong metal angle to support that reveal so that we don't have to tie it back to the steel stud backup wall, because that would create additional thermal bridging. And you can see that the isotherms in that detail are a lot, you know, a lot nicer, a bit smoother than the ones we've seen for parapet, and the, you know, the total, the result psi value is actually, you know, pretty good. So having said that, that was a kind of flavor as to what it takes to look at high performance in passive house building enclosure. So I wanted to summarize a little bit on the enclosure and I guess the overall series. With high performance and passive house enclosures, we need an integrated approach to that facade design, right? You understand that because you can see that for the details that I've shared, it's not just the enclosure consultant, it's not just architectural, it's we have to look at a lot of different perspectives, be it cost, aesthetic, thermal performance, structural strengths and wind loads and other types of loads that the cladding you know, might experience. So without that integrated design approach where we are looking at every single perspective and optimizing as a result, it will be very difficult to achieve the performance that we're after. And when I start zooming in terms of high performance targets that we have with the stringent, you know, stringent energy and carbon targets, if you want to deliver great walls, you know, and great windows, if I focus on the walls for a second, you really want an early understanding of all the little derating elements that you're going to have, be it insulation fasteners, cladding attachments, you know, steel stud backup walls, all of that adds up, and you want to plan from it. You want to plan for it from day one, rather than have a surprise later on, and you know, make it that you don't meet the stringent performance targets that was required out of your design. Finally, you saw for the rigid detailing, be it for parapets or window insulation or frankly any detail, you need extra care and good detailing. And then you saw that the window installation has the potential to have a significant impact simply because of the sheer amount that you might be facing depending on the typology that you're designing. So really the way we're designing facades, but also designing everything, we're working with every single discipline with the use of the integrated and highly collaborative, which means a lot more communication than we're used to. If we start changing our design approach, we have all the tools at our, you know, and all the skills at our disposal to start delivering high performance enclosures and high performance buildings as, you know, the new norm, which is where, you know, most regulations at all kinds of different levels, both in Canada and the US, are pushing us at the moment. So that's it for today. Just before we close that 3-part series, I also wanted to give you just final pointers if you start, if you want to start interacting with the community. I have to say the Passive House community is very generous with the amount of information that gets shared. We're really welcoming of new people so that they don't have to reinvent the wheel. We try to give them all our knowledge to get a head start so that people can do different mistakes and keep, helping the industry advance. So if you want a few additional courses, I'd recommend going to the Passive House Canada website directly and look at all their courses. You have anything from a very, slightly deeper but half day to 1 day introduction, all the way to the full, you want to become a certified Passive House designer, then it's all in there. And also in terms of just interacting with the community, I think that both the conferences in Canada, which is in Hamilton next May, and in the US, which is in Denver in October, are lovely ways to start interacting with the community. The final thing, which I didn't put on the slide, but I'm just remembering, is if you go to the Passive House Canada website, they also have a quarterly social event in all, in a few main cities, so Vancouver, Toronto, and Halifax for now, and I think a few will be added in 2023. And so if you just want to have a nice social evening with a bit of technical presentation, go onto their website, sign on to their newsletter so that you can keep track of when is the event in your city, and you can attend that. Just as a quick example, the next one for Toronto, I'm based in Toronto. The next one is on November 30th. It's free, everything is covered for that small evening. So if you feel like starting to dive into the Passive House community, then don't feel shy and come and join us. So, Romy, that's it for today. Let's see what we have in the Q&A.
Okay, that was wonderful. Thank you so much for that very informative session and for the 3-part series on Passive House 101. So if any members have any questions that you have for Maureen, kindly place them in the Q&A and I can read them out.
Sounds
I'll
good.
give you a few moments for that.
And Milton, just to answer your question, I believe the links are circulated afterwards. So for sure, the recordings are there. We were recording the session, so you should be able to, review any of the 3-part series afterwards, which is great.
So we currently do have the links posted on the chat forum here on the meeting, if you'd like to copy those. And I'd be more than happy to share that information with you afterwards when we send you your credit email.
Perfect.
So we don't have any cute questions just yet. Should we wait another minute, Maureen? Would you like to?
Yeah. Let's wait. It's okay. We still have a few more minutes, and so don't feel shy about asking any technical questions. I love that too. And if not, that means I did such a great job that everything was like 100% clear. Is that
exactly? Yes. So in the meantime, I just wanted to let everyone know how you can get your Con Ed credits. If you've provided your AIA number during your registration, your AIA credit will be reported by us for you on your behalf. You can send an email to the CEU at AIACanadasociety.org if you have any questions. And you will receive an email 24 hours after today's session that you can later on print off as a PDF, and you can self-report for any other organizations that you may require it. In addition, I also want to remind you that tomorrow we're having our 4th annual AGM, at which we're going to be announcing our design winners for 2022. So we welcome you to join us.
perfect? Thank you, Romy. I think
I think you did a stellar job. That everyone is just
There's one question, one
Oh.
technical question in the chat.
Okay.
I'm just going to repeat it. Not everybody can see it. How does the Passive House results compare to the NCB 2017 levels or 2050? Okay, and that is a kind of really good question. I'm going to tackle it really quickly. You guys can still see my screen, right?
Yes.
Yep. Okay, perfect. So what I want to first highlight is that the NECB paths, right? When we look at the default, not the default, but I guess the performance path that we're looking at, the performance path is set with percentage better than reference building, which makes it really hard to compare two buildings at a time, because the reference, the baseline model, the reference model might be different, right? And so the percentage better than is, you know, it can work if done properly, but on average, a lot of literature review, it's been showed that it doesn't deliver as good performance as working with absolute target does. So the first thing I want to highlight is back on the screen, even if this is Passive House, but the same thing applies with the Toronto Green Standard, with the BC Energy Step Code, with the Massachusetts Stretch Code, and all kinds of other regulations. They have or are all switching from a referenced approach, so percentage better than baseline, to an absolute metric approach, which is, as you can see on the screen, your building should not use more than X amount of energy, right? In kilowatt hour per square meter per year, or kilo BTUs per square feet per year for our friends in the US, right? And so based on that, I would say the apples to apples comparison is not possible. However, we do know that Passive House pushes, you know, Passive House is, with all the regulations we've seen, Passive House is, you know, from a high level, equivalent to the end goal that we're getting to for policies, you know, for the new regulations, the policies that are aiming to cut energy consumption and greenhouse gas emissions. So these targets are extremely stringent, and most of the time Passive House perform extremely better than the standard NECB 2015 and 2017 required. So we are way past that. Side note as well, most of the time for code compliance, we can take the prescriptive approach to meeting code, and we do meet them, because Passive House will ask you to design by default at a much higher performing level than what you would typically have. So that's just to give you a sense of, this is NECB 2015 and 2017 is kind of where we are right now, but it does not yet reflect where all the greenhouse gas emission reduction regulations are driving us. So really good question, really tricky to completely answer in a short amount of time, but I hope that I gave you know, an okay overview of, like, first of all, it's not apples to apples, but second, Passive House is equivalent to the end goal that most regulations are setting for delivering climate action for the buildings we have. Okay, cool. Thank you for the thumbs up online. Okay,
well, great. Thank you so much,
cool.
Maureen.
No worries at all. You have my email if you need anything else. So you have, you know, AIA's contacts for Dora and Romy. So thank you again for taking the time today, and I sure hope that I cross paths with some of you sometime soon. Okay.
Excellent.
Okay.
Thank you, Maureen.
Bye.
And thank you, everyone, for attending today's session, and for those who attended all the sessions, thank you very much as well. Once again, I'd just like to let you know that part 1 and part 2 links are on the chat forum, and I'll make sure to include them on your follow-up email with your credit information. And once again, please join us tomorrow, Wednesday, November 23rd, for our AIA Canada Society Annual General Meeting, at which time we will be announcing this year's 2022 Design Award winners. Thank you very much, and have a great day. Bye.